In this video, we'll take a look at carbocation stability. Now, this is a very important topic, especially for predicting the products and intermediates of an electrophilic addition reaction, and we'll revisit that mechanism as we go along. So the order that you need to have memorized is listed here. It is tertiary and benzylic are the most stable. These are approximately the same. They are more stable than secondary and allylic, which again are approximately the same, which is more stable still than a primary, more stable than methyl, and more stable than vinylic. Now, an example of each one I've listed here. Here's a simple tertiary where methyl groups are substituted at the carbocation 3 times. So the general trend here is more substitution results in a increasing stability of the carbocation. That is why this tertiary is more stable than the secondary, more stable than the primary and the methyl. Now, reasons for that, we'll get into the explanations, but you need to be able to recognize tertiary versus secondary carbocations, and the easiest way to do this is simply count the number of carbons that are bound at that carbocation. So this is why this is tertiary. If we look at that center carbon bearing the positive charge, it is bound to 1, 2, and 3 methyl groups, 1 to the left, 1 to the right, and 1 up. This is 3, and thus tertiary carbocation and would be the most stable. And benzylic is the position in which a carbocation is adjacent to a benzene, and this has excessive or extended resonance that we'll take a look at. Here we have a secondary carbocation. Again, count the carbons bound to the carbocation directly, the carbon bearing the positive charge. That is the center carbon. To the left and the right, we have 2 methyl groups, 1 on each side, and then a hydrogen that is implied but not drawn, so that would be a secondary carbocation. Here we have allylic. Allylic is the position that is adjacent to just a pi bond. This could be an extended conjugated system, not necessarily just one pi bond like this, but it can't be a benzene ring because that would then be benzylic. If you had extended conjugation, that would be more favorable than just the allylic because of the extended resonance. All right, then we have primary here. This is bound to just 1 carbon at the carbocation position. It doesn't matter that there's 2 carbons in the chain that is bound to the carbocation. You still just consider that primary. And then, so that is more substituted than a methyl group, which contains no carbons at all besides the one that bears the carbocation. And then lastly, we have the vinylic carbocation. This is the least stable. And the reason for this is semi-special. It's different from all the other ones, but this is the least stable because the carbon bearing the positive charge is sp hybridized, which is doesn't allow for hyperconjugation, which we'll get into that effect as we go along in the video. But essentially, it's due to the hybridization, the sp hybridized versus sp2 and all the other cases, that this is such a poor intermediate and poorly stable carbocation that is very unlikely to form. Now, getting into the explanations for why this trend is what it is below. There's 3 major explanations depending on what you're comparing. First and foremost is hyperconjugation. There's also the inductive effect, which is kind of similar to hyperconjugation, but it's more general. And then, of course, there's resonance, which we've already discussed a little bit in regard to the differences between allylic and the benzylic carbocations. But now, let's take a look at the hyperconjugation. So the general idea of hyperconjugation is if you have the carbocation, that carbocation's positive charge is localized more or less in the empty p orbital of the carbon, because that carbon is lacking its 4th bond. It's lacking an octet, and that's kind of where we say the positive charge is residing. So that empty p orbital can form a new atomic orbital with the sigma, or the single bond of a carbon hydrogen that is coplanar, that is in the same plane. So when you have this type of orientation, the sigma bond of the carbon hydrogen can interact with this p orbital that is empty in the carbocation, and this results in a stabilization effect of that carbocation, because sometimes the electrons from this carbon-hydrogen bond that's adjacent is more or less being donated to that pi bond. It's forming this new interaction, new atomic orbital, which is overall lower in energy than just a localized positive charge. So this is the general idea of hyperconjugation. Now, one thing to mention here is when you have a carbon-hydrogen bond like this, it's free to rotate. So each of these hydrogens can be coplanar with the empty p orbital at any given time. So the more of that you have possible, the better the hyperconjugation will be, or the more hyperconjugation that is present, which is why the increasing substitution there would allow for an extension of this hyperconjugation effect. Another thing to mention is it doesn't have to be a carbon-hydrogen bond that performs this hyperconjugation. It can be specific carbon-carbon bonds that are also in this coplanar orientation. So like, for example, if this was a methyl group, this carbon-carbon bond could still be donated there, and that would cause something that's called a rearrangement, but you get very similar effects. So that is the general idea of hyperconjugation. All right, the next explanation to talk about is the inductive effect. Now, the inductive effect is an electronic effect, meaning how electrons are moving or how they are being influenced by some particular substituent. So we can normally, or traditionally, you think of induction as if you have an electron withdrawing group nearby that is going to pull the electrons away from whatever you're looking at. So like, for example, in determining acid strength, the inductive effect, if you had like a nearby fluorine or other heteroatom, that will remove some of the electron density from the XH bond or whatever the acidic proton is, and that will increase the acidity of that proton because you have a less electron density there. But that same exact phenomenon can be talked about if you have an electron donating group. That would then oppositely, it would move the electron density towards the center that you're looking at. So like, for example, if we're using pKa's, same idea, using acid strength, if you had a electron donating group that was nearby, it would donate electrons to that XH bond and make it less acidic because there's more electron density there. It's harder to break that bond. So now getting it back to carbocation stability, using the same idea of the inductive effect, is that alkyl groups are known to be weakly electron donating. So because of that, if you increase the substitution at a carbocation, you will get more of this weakly electron donating effect towards the positive charge, which in essence distributes the positive charge amongst more atoms, and that is in general more stabilizing. We know that a general concept in chemistry is if neutral atoms are more stable than charged counterparts, similarly charged atoms, if we can disperse that charge through an effect like induction or some other electronic effect, that is favorable and overall decreases the energy of the global system. You can think of this kind of like resonance as well, in the fact that in resonance you're moving the positive charge or negative charge, you're moving the charge to different atoms, which we know resonance is a stabilizing effect, and it's for that exact reason. So now the inductive effect is similar in that way, in that the methyl groups here are weakly electron donating, which we can then show that there is some amount of electron density going towards the positive charge, which ultimately results in some amount of partial positive felt on both, or excuse me, all three of the alkyl chains. And what this does is alleviate some of that positive charge that is localized on the carbon. So the more substitution you have and the more you can donate towards that carbon, the overall more stable that carbocation is. Now, this is all rather technical jargon, but the way I've memorized this and use this as going forward is just think about your carbocation as like as a bridge. And all of your alkyl groups that are on that bridge are the beams that are supporting it, the pillars that are supporting the bridge. So the more of those pillars that you have, the more alkyl groups you have, the more support the bridge has, and ultimately the more stable it is, the lower in energy that it is. Now, this is the technical definition for that, but I like the bridge analogy just to have something that I can tangibly think about as I move along in trying to solve problems that are similar to this. So this explains the substitution effect, so like primary versus secondary versus tertiary, that trend. But the last explanation explains resonance, which explains the difference between benzylic and allylic and how those fit amongst the list of carbocations. And the idea in benzylic and allylic is you have resonance structures that are available. So for example, you can delocalize this pi electron into the ring, or excuse me, out of the ring to stabilize the carbocation, creating that, moving the carbocation here. And then you have two more structures. You can move this pi bond here. And lastly, you can move this pi bond down like this. And this concludes the resonance structures that are available. Now, if you wanted to rank these resonance structures, this is definitely the most stable or most contributing, simply because it's aromatic, and all of the other ones break aromaticity due to Huckel theory specifically. And but nevertheless, you have this extended conjugation. Now, it will depend heavily on what the specific atom is. If you wanted to compare a benzylic carbocation to, say, a tertiary carbocation, in general, those aren't going to be in the same series that you're asked about because they're just so similar in energy that it's difficult to distinguish. But what you could distinguish is if you had a benzylic versus allylic, for example. Here's our next question. You should be able to rank these simply because of the number of resonance structures, because here you only have one additional one. You start with one resonance structure and you can only draw one more. Here we start with one resonance structure and we can draw three more. So the benzylic carbocation is much more stabilized because of this extended resonance. Now, let's say you had a extended conjugation. You had a conjugated carbocation like this. Now, this is going to be more stable than just the simplest allylic because you have now two additional resonance structures that you can draw. So the main point that I'm trying to make here is the number of resonance structures is extremely relevant. It's not just is there resonance or is there not. That's where you should start, but you need to be able to quickly draw all the resonance structures so you can determine which molecule or which intermediate has the most resonance structures, because that is going to be the least lowest energy, the most stable, and therefore it's going to be the most likely intermediate for whatever your reaction is. All right, for the remainder of the video, we will take a look at several example questions kind of tying all these ideas together. So first is the simplest type of question along these lines, just rank the following carbocations in order of increasing stability. So here we have a series of different substituted carbocations. And we simply, for this type of question, you just need to determine the substitution and then rank those in order of increasing substitution because we want increasing stability. So to do that, you count the number of carbons that are bound to the carbocation. So here we have the center carbocation, 1 carbon, 2 carbon, and 3 carbons. So this is tertiary, a very stable intermediate. Same thing here. We have 1, 2 carbons bound at the center. So this is a secondary carbocation. Here we have only 1 carbon bound directly to the carbocation. Doesn't matter that there's 2 here. It's just how many carbons are bound directly to the center. So this is primary. And then we take a look at this one. Here, this center would be quaternary, but this is not the carbocation. The carbocation is out here. It's only bound to this 1 carbon, so this is also primary. Now, so let's call these. Let's call this molecule 1, 2, 3, and 4, just to list them without redrawing the molecules. So the least stable is definitely 3 and 4, and they're going to be about the same. Now, you could make the argument that 4 is probably a little bit more stable because it can have a methyl migration, but we'll save that for a different video. So for here, for this purposes, and in general, you would say that 3 and 4 are about the same. But these are definitely both less than 2, which is secondary, has extended hyperconjugation and a more inductive effect through the donation of the electron donation of the methyl groups, the alkyl groups. And then using the same logic, this is why 1 is the most stable because it's tertiary, has the most hyperconjugation, and the most induction. All right, here's our next series. Same idea, we're primarily comparing substitution here. So if we look at this first molecule, we have a carbocation that is exocyclic up here, and it is bound to only one carbon. So this is a primary position. Here, there's 3 carbons, 1 carbon down, 1 left and up, 1 up and right. So this is a tertiary carbocation. This is an allylic carbocation, which is adjacent to a pi bond, carbon-carbon pi bond. This is approximately the same stability as a secondary in general. So we would still be able to determine that the tertiary is more stable than the allylic. This one is vinylic, which is extremely unstable. This is even less stable than a methyl carbocation. Again, recall the reason is that this carbocation is in an sp hybridized orbital. So there's not as good overlap that is possible for hyperconjugation or induction. So let's again list these molecules in numerical order, and we want increasing stability. So the vinylic is definitely the least stable, followed by the primary, followed by the allylic, which is about the same stability as a secondary. And then this is less than the second molecule here, which is a tertiary carbocation. That's the most stable option. All right, here we have another set of questions. So again, we're asked just to rank the carbocations in order of increasing stability. So we need to look at substitution and benzylic or allylic positions. So here we have what appears to be a primary carbocation because it's only bound to 1 carbon, but it's adjacent to a benzene. So this is benzylic, which is approximately the same as a tertiary in terms of energy and stability. Okay, so what about the next one here? The next one, we have a secondary position, nothing special. It's just a carbocation center is bound to 1 carbon down, 1 up and right. So that is a secondary position. What about this one? This is allylic. This carbocation is adjacent to a carbon-carbon pi bond, so there is resonance. This is about the same as a secondary carbocation. And this one is primary. This one, again, is kind of deceiving because you have a quaternary center here, but this carbon, the carbocation is on the terminus here, so it's only bound to that 1 carbon. You don't count all of the other substitution in this ranking system here. So now again, let's just name what these molecules are numerically so we can describe them. So the least stable is definitely the primary, which is less stable than the secondary, which is about the same as the allylic. So 2 and 3 are about the same. And then definitely the benzylic is the most stable, again, because of the extended resonance. The allylic has 1 resonance structure, which is why it's about the same as the secondary, but still less than the benzylic position, tertiary. Okay, now let's take a look at our next set of questions. So here, I didn't write a prompt, but the question really is to draw the mechanism and explain why the intermediate forms. I mean, this is just a simple Lewis acid, Lewis base reaction, nucleophile, electrophile, and we need to determine where that hydrogen is going to go. Because what we have is a nucleophile here, or Lewis base, at the pi bond. The carbon-carbon double bond is electron rich. This is a good, decent nucleophile. We have a strong acid, H+. This could be supplied from like H2SO4 or HCl or something along these lines. But the point is, this is a very good electrophile. It is even positively charged, so it's Lewis acid. So this is a simple Lewis acid, Lewis base reaction. But now the tricky part is we have 2 carbons that are a part of the pi bond, part of the carbon-carbon double bond. So that hydrogen couldn't go at position 1 or position 2. And the only way to determine where it goes is to initially draw both of them and then determine which is the more stable carbocation, because that is going to be where the lowest energy path is found, which is what's going to happen in terms of predicting the product. So if the hydrogen were to go at position 1, you would get the carbocation at 2. If the hydrogen were to go at position 2, you would get the carbocation at position 1. Now, if you're wondering how I did that, if you put the hydrogen at 1, that means you're using the 2 electrons from the pi bond to create that sigma bond that's drawn in the carbon-hydrogen bond. And those 2 electrons are now gone, or they're not gone, but they're preoccupied in binding the new hydrogen, the carbon 1 and the hydrogen. So what that means is carbon 2 has just lost those 2 electrons completely, and that's it. It hasn't gained anything in return, so it simply takes the positive charge. Similar argument for the other position. If the hydrogen were to go at carbon 2, again, the pi bond, 2 electrons in the pi bond are preoccupied with the carbon-hydrogen bond there, carbon 2 to the hydrogen, so carbon 1 gets the carbocation. Now, this is tertiary and this is primary, so this intermediate is not going to form. This is not the correct intermediate. This is what's going to form. Okay? Because it's more stable, lower in energy to form. So then if we had a different nucleophile, let's say we had some water floating around, or a halide like Cl- or Br-, that will attack that tertiary position and get your final product. But again, the main point I'm trying to emphasize here is you can predict the product and intermediates that lead to the products based on carbocation stability for electrophilic addition mechanisms and others, but the simplest form in which this applies is the electrophilic addition. Now let's look at one more example along the electrophilic addition mechanism. So it's very similar. You have a endocyclic pi bond now, meaning internal pi bond in a ring, compared to exocyclic that we had before, meaning outside the ring. But here, is there a difference in where the hydrogen needs to go? Is there a difference in the carbocation? And again, like I initially mentioned, what you should do is draw both of them to start, both options, and then rank the stability. So if I put the hydrogen at carbon 1, I'm going to get a carbocation at position 2. If I put the hydrogen at carbon 2, I'll get the carbocation at position 1. These are both just secondary cyclic structures, secondary carbocations of a cyclohexane. So there's no difference. So these are identical. So here you didn't need to rank them and determine which one was most likely. You're going to get either one, and this is going to give you the exact same product, right? So if you're going to name this, you will start the naming system at the same position. So there's nothing different between these two structures. So your product is going to be exactly the same. So you have to kind of keep an eye out for that. You should always just determine if the hydrogen goes, which carbon it goes to, and then why there's a difference in the product or not a difference, like it's the case here. So that is all I had planned for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or any other comments or any suggestion along these lines, please feel free to leave it in the comment section down below, and I'll get to you as soon as possible. So with that, I hope you all have a great day, and I'll see you in the next video.